All right, so this problem is a law of conservation of energy type problem. So when you can identify it as that, and it's usually the case when you're going from like one position to some other position. Sometimes work is being done in between getting there. If work was done prior to the start position, then you don't count it. If the work happens in between where you're counting the start position and where you're counting the end position, then you do include it. So in this problem, I would always begin by writing the formula that combines the law of conservation of energy with the work energy transfer theorem. So that includes the possibility of work being involved. So here's your equation. So if we look at this, we see that a bike reaches the top of a hill with a speed of 3.2 meters per second. All right, so I don't know at this point whether they're going to call that the original or the final position. I need to read further. It says that the bicyclist did not pedal while on the hill. How fast is the bike moving when it got to the hill? So that means that these numbers right here, the 5 meters and the 3.2 meters per second, these have to do with the final position. Since the person did not pedal while on the hill, so the bicyclist did not pedal while on the hill, then that means that there was no work being done. So there was no work being done between when the person got to the hill and when they got to the top of the hill. So they had enough energy at the bottom to get up and over the hill. So what we do know is at the bottom of the hill, they're at the lowest position. So if the hill is 5 meters high, then when they got to the hill, they were at the low point when there was no height to the hill. So this is also going to be 0. So in most of these problems, something, usually one or two things, at least cancels out as 0. So once I have it like that, if you notice again that they're giving me the height, they're not giving me the potential energy. They're giving me the velocity, they're not giving me the kinetic energy. They're asking for how fast, which is velocity. So what I'm going to do is I'm going to take this equation right here and I'm going to replace the original kinetic energy with the formula for kinetic energy. So the original kinetic energy is 1/2 mvo squared. Now I'm going to replace the final kinetic energy with 1/2 mvf squared. And I'm going to replace the potential energy with mg times the final height. So this is the equation that I now have. And if work is not involved, then they don't even have to give me the mass. Because it doesn't matter what the mass is of the object, because you can see here that since it's in every single term, I can cancel it out. And now all we're going to do is just solve this for the unknown. And the unknown in the problem is, how fast was the bike moving when it got to the hill? So that's the original velocity. So I just need to solve this for the original velocity. I'm going to multiply everything by 2 to get rid of the fraction. Anytime there's a fraction, just get rid of the fraction right away. It's easier to then move things around. So I'm going to get VO squared equals VF squared plus 2 GHF. And if you look at it, it looks a lot like a formula that we've seen before. VF squared equals VO squared plus 2AS. So because it is very similar to that. That's really where it comes from. So solving for VO. So VO is going to be the square root, always plus or minus, the square root of VF squared. Whoa. Come on. VF squared plus 2 GHF. Plug in the numbers and you'll have your answer. So these problems are really not that complicated. I mean, once you've identified the things that you can cancel out, it's fairly straightforward. So VO, again, it's plus or minus, but if you remember up here, it's saying how fast is the bike moving. So we're just looking for a speed, and in this problem, direction wouldn't really be a factor anyway. So we're going to have VF squared plus 2GH. And I've got to look back up here and see. So the speed was 3.2 meters per second. G is 9.8 meters per second squared. The height is 5 meters. And now you can tell that this part right here, is going to make the, like if it was only this, then we'd get 3.2 meters per second, because the square root of 3.2 meters per second squared would be 3.2 meters per second. So this is the part that means we have to be going faster, because we're going to lose that amount of potential energy as it goes up. So we should obviously have a faster speed when we're at the bottom of the hill than what we're going to have at the top of the hill. And when you solve that, you get, what, 10.4? 10.4 meters per second.